So yeah, I guess that was a great introduction. Thank you, Sebastian. As he said, I'm a PhD candidate at the University of Colorado in Boulder. I'm going to talk about the reference open source controller today, or ROSCO, which has been certainly a major part of my PhD research. I'm going to start off, this presentation is by me. I think this controller certainly has been a big part of my PhD, but has also been, there's a lot of other people that have contributed and are continuing to contribute, and maybe some of you guys will also be on that list in the future. Okay. So I'm going to start with some acknowledgements, kind of in that trend of this being a very collaborative project. First, I want to thank Dan Zalkind. He started at NREL about a year ago and has been very important to bringing ROSCO to be kind of so robust and well used in the way that it is now. TU Delft and the Delft Research Controller, I'll talk about this a bit more, but Sebastian and his PhD advisor, Jan Willem, kind of maybe laid the framework and put the bones down for what is now ROSCO. So I'd be remiss if I didn't thank them. The Wind Energy and Integrated Servo Controller, the WEIS development team at NREL has really put it through its paces, and I think done a good job of finding pretty much every bug that has been found by someone that isn't myself or Dan. My advisors, Lucy Powell and Alan Wright at Boulder and NREL. And then last but certainly not least, all the users. So I set up about a year ago Google Analytics on the documentation page, just to kind of get an idea of if it's being used and how it's being used. And this is a 30-day average, and it's kind of taken off, which is exciting, especially since maybe the most recent paper about ROSCO came out and this conference series was announced. So that's certainly a lot of people and a lot of people around the world, which is very exciting to see. So what is ROSCO? Generally speaking, I'd say it's a framework for tuning and implementing a wind turbine controller. I think that's been kind of mentioned a few times. It's in the bladed style DLL and Simulink implementations. So that means that it communicates well with programs like OpenFast, Talk2, and Bladed, of course. And then also any kind of interfaces with Simulink that you might have in wind turbine models that interface with Simulink. There's a kind of whole automated tuning process, which I'll talk a bit about, and that it gets at what Sebastian mentioned in the introduction, and that it's a kind of built to be easy to use, and for users that aren't necessarily controls engineers to get a controller working well. It has some modern controller features, and I'll talk more about that a bit as well. And kind of maybe within that umbrella, controllers for floating wind turbines and some active aero devices, specifically trailing edge flaps, but somewhat generically speaking, active aero devices. And as I said, very actively developed here, and check it out. Check it out on GitHub. So a little background on maybe reference controllers and what really existed, especially when ROSCO was getting started, and still somewhat exists to this day. The NREL 5 megawatt controller, I think most, if not all of you on this call would be familiar with. I'd say maybe this has some basic control features, but nothing was particularly advanced or modern about that, especially within the context of today's controllers. And this is still distributed with OpenFast as Fortran code itself. So maybe my point being that if you wanted to change it, you have to change the code and recompile always. Kind of similarly, an evolution of that a few years later was the DTU 10 megawatt controller. Speaking in blanket terms, I'd say this maybe had some basic plus control features. There's an asterisk here. There's been a ton of work on the DTU 10 megawatt controller since 2013, and even in the last maybe 4 years or so that ROSCO has been being developed. So I certainly don't mean to undermine any of that work. This is distributed through DTU directly, and also, as far as I understand, more or less as Fortran code as well. A few years ago, the Delft Research Controller came out from Sebastian and Jan Willem. And in my mind, this kind of collected a lot of maybe the best aspects of the NREL 5 megawatt controller, put them together in a really nice package, add some stuff on top of it. This was distributed through GitHub, like a lot of modern codes are. And this was written in Fortran, but kind of laid the framework for an input file. So This meant that if you wanted to change, say, your tuning gains for the pitch controller, then you just have to change an input file. You don't have to go through and recompile code. And that was kind of a big, in my mind, a big step for usability that is part of ROSCO now, and is, I think, helps a lot. So maybe this little bit of a graphic to talk about where ROSCO fits in all of these. So if we think about these, again, blanketly speaking, these NREL 5 megawatt and DTU 10 megawatt controllers existed and kind of came together to the DRC Fortran in a lot of ways. I'd say ROSCO at this point has kind of includes all of what the DRC Fortran has and has had a few years of development on top of that, adding features, fine-tuning features, kind of refining the interfaces and things like that. So that's maybe kind of where ROSCO lives, and then around so ROSCO built then to communicate with the turbine or simulation software, but around ROSCO exists what kind of we colloquially call the ROSCO toolbox, and this primarily includes these automated tuning methods that I've talked about, and so this kind of feeds directly into ROSCO, and I'll talk more about that interface in this talk today. But this basically enables either a computer or a person to tune this controller pretty easily, I think. You can set up optimizations, or you can do your best to optimize in your own head. So talking about some of these controller features and these modern controller features that exist. So we maybe start with a wind turbine and have kind of our common controllers here, a blade pitch controller, both collective and individual pitch control do exist in ROSCO, as well as a generator torque controller. Kind of traditionally, the K omega squared law is used. I'm happy to talk about these kind of logics more in detail if you want. I'm kind of speaking at a high level here. There's also a tip speed ratio tracking controller that exists for below rated operation, and the generator torque controller also can control constant power and constant torque above rated operation. This tip speed ratio tracking controller, it's necessary to have a good wind speed estimate. So in ROSCO, there's a wind speed estimator, and then kind of it's, I think, fairly well known that the transition between these two controllers can be a bit dicey sometimes, or there's a lot of loads kind of at that inflection point on the power curve, and so there's a set point smoothing logic to help that out. There's also, we've added some pitch saturation, and this can help with thrust clipping near rated operation and some power maximization and low wind speeds. And I'll show some brief results on that just to give a teaser, I guess. There's some shutdown controller logic wrapping this up. There's floating feedback terms that exist, active arrow control that exists, and yaw control that exists. And this all comes together into maybe what I'd say is kind of a primary block diagram of ROSCO. What's not shown here is a lot of filters and switching logics and things like that to kind of help all of this work smoothly and work, especially as these features start to add, kind of trending towards what we know of as kind of standard industry controllers of today. So just to talk about some of these features a little bit more, I'll talk about the pitch saturation logic. The idea here is that we can impose minimum blade pitch schedules to kind of help improve performance throughout the operating region. So on the left side here, can you see my mouse? I guess maybe if I laser it, then.
Yeah, I can see your mouse.
Yeah. So on the left side here, we kind of have what this blue curve showing kind of what we expect our steady state pitch operation to be. And then this red line here is where we can impose a minimum pitch saturation. So you'll notice in low wind speeds, we actually pitch the blades. And the reason for that is if we look at our power coefficient surface and these kind of higher tip speed ratios, we notice that it's actually our power coefficient is higher if we pitch our blades. So in a case where this is the case for the IEA 15 megawatt reference wind turbine, we're at low wind speeds, we actually have a minimum rotor speed constraint. So at cut-in wind speed, we're actually operating at a higher tip speed ratio than optimal. So in that case, we pitch our blades, and that kind of increases our power a little bit. Similarly, near rated operation, you can see this minimum pitch schedule kind of starts the pitching early, make sure that we don't actually kind of operate in this grayed out area here. And functionally what that does is it kind of clips off the top of the thrust curve. So within ROSCO, the tuning methods, we can say that we want to cut off 10% from our peak steady state thrust. And that can help reduce tower loads and increase platform stability for floating turbines. So looking at kind of a brief time history here, these plots come from the most recent paper on ROSCO and wind energy science. There's kind of this gray line in the back is our wind speed. We notice that if we increase our blade pitch angle here from the red to the blue curve in low wind speeds, then we increase power a little bit. Kind of, as we said, moved up that CP surface a bit. Similarly, in near rated wind speeds, if we saturate and kind of follow this red saturation line here, then we can we reduce our thrust a bit below this maximum thrust amount. Some kind of brief results to talk about maybe what comes of here. This is from design load cases 1.1 and 1.3. You notice kind of the platform pitching angles for the IA 15 megawatt reference turbine. The blue is kind of the full ROSCO with everything. The red is if we were to take away this pitch saturation, and then the gold is if we were to take away the floating specific feedback. And we see that both, generally speaking, the pitch saturation and the floating feedback help stabilize the platform a fair amount. This kind of manifests itself in reduced damage equivalent loading at the tower base. And also kind of as we'd expect, those of you familiar with pitch saturation, that does mean that we do take some power losses, where if we didn't have the pitch saturation, we would get a little bit more power near this kind of knee of the power curve. So this is all kind of maybe what we'd expect, and is nice to see there. So what's on the horizon for ROSCO? What's to come? So there's some open loop feed through, and this can be used. There's some work ongoing for open loop optimal control. And so say you know your wind speed, you know what the simulation conditions are going to be, what your future disturbances are. You can just kind of feed through using ROSCO maybe as kind of an interface to a software like OpenFast. Some tower resonance avoidance schemes kind of exist. I guess I might say that all of these things maybe semi-exist in various branches of ROSCO right now and are making their way into the main branch. And so this would be for avoiding kind of excitation of the tower at a 3P frequency, often needed if you have kind of a softer tower design. Some power reference tracking, and this can improve above rated power capture. For example, if you know that you can kind of push that limit towards your maximum rotor speeds a little bit more, you can try to eke out a little bit more power. There's some robust stability constraint tuning. This can improve the floating wind turbine dynamics and include the ideas of linear models and linear analysis into the tuning processes a little bit more. Some external controller interfaces. I've actually worked with Bart a bit on getting kind of 0MQ, a super controller sort of interface between ROSCO and Python, and that kind of allows a super controller for something like a wind farm or wake steering study, or if you had a separate DLL, kind of emulating an idea where you have a single frozen turbine and then turbine controller and then kind of a wrapper controller around it, which often exists in industry. Yeah, and I guess what else? I think this is, again, I'd like to reiterate, this is a community-driven project, and whatever people would like to see, and especially would like to contribute, would be great to add. Looking at this from kind of a workflow perspective, and how this whole ROSCO tool chain comes together. So we kind of start with the turbine model here, and for me, generally speaking, this is an OpenFast model. We'll simulate the turbine, and of course, simulating the turbine means communication with the controller, and that's with ROSCO itself. This controller takes an input file, which I'll talk about a little bit, and then the ROSCO toolbox tuned this input file. To kind of make this all easier, there's some inputs that get passed to the ROSCO toolbox. You could think of this as like maybe a parameterization of what you want your final controller to look like. And then, of course, some important parts of the turbine to be able to accurately tune things well. Looking more at this controller input file, There's multiple sections, multiple modules, multiple flags to enable and disable these features. I won't walk through each one of these, but you can see what type of torque control do you want to do? What type of yaw control do you want to do? Do you want pitch saturation? That sort of thing. If we look deeper into just as an example, the pitch control section here, this has kind of maybe what we'd expect, a number of gain scheduling entries, the angles for the gain schedule, PID gains for that, for each angle, and those just get basically interpolated in practice. Some other sort of necessary parameters are pitch limits or max pitch rates, reference rotor speed. But if we look at these just at the schedule here and look at our angles, our proportional integral gains, which is kind of maybe our standard pitch controller. This can be a huge array that is 20 plus entries that need to be tuned, that maybe historically has taken a controls engineer to pick that out. We look at the file as a whole, it's a huge file. This is just a screenshot. I couldn't take a screenshot small enough that this was legible. So there's a lot going on, right? And that is kind of daunting and challenging to someone that's not a controls engineer. So that's where this tuning inputs file comes in, and this kind of parameterizes things, makes it easy. So this kind of points to the open fast model in the ROSCO toolbox sense, really points to your own turbine model if you needed to. And again, there's some sort of flags. We need some basic turbine parameters like rotor inertia, rated rotor speeds, some cut in, cut out wind speeds, those sorts of things. But then we can just look at a handful of necessary tuning parameters. So we have some wind speeds to schedule at, desired natural frequencies and damping for the above rated, and the below rated if you want to use the tip speed ratio tracking controller. And then there's some optimal tuning parameters. These are just two examples. If you have a minimum rotor speed constraint like the IA 15 megawatt, if you would like to do some peak shaving, how much peak shaving would you like to do? If you don't enter these, basically there's defaults that are kind of maybe standardized there. I'd like to point out here, there's a kind of maybe historically or familiarly, there's generally the pitch controller will have a single natural frequency or damping that's defined. We've done some work to kind of make it possible to schedule this across wind speeds. So in this case, at 14 meters per second and 20 meters per second, there's a natural frequency and damping that's desired. And what that ends up with is kind of a gain schedule that looks something like this, where if we look at our natural frequency, we start at 15. This kind of has a sigma interpolation up into higher wind speeds, and this results in these gain schedules that we see here. This kind of opens the window, having a parameter file like this to look at optimization. So within NREL, the WEIS toolset, or the Wind Energy Integrated Servo Control toolset that I mentioned earlier, this is kind of all wrapped up in there, and we can optimize pretty much any of these major tuning parameters that go into the ROSCO tuning process and run these optimizations. And so this is very maybe fresh ongoing work right now. And this is exciting, just kind of maybe as a, oh, it's not work. Sorry about that. It seems to have frozen. Kind of as a brief teaser result here, we can see that if we have the optimization objective of minimizing our tower-based damage equivalent loads, we can bring these down a fair amount, kind of satisfy a rotor speed constraint here. This is implementing some of the robust stability constrained tuning methods that I kind of briefly mentioned. The point being, we can kind of wrap these up in an optimization, put them through iterations, and bring down loads or maximize AP or whatever, so be it, that we would like to see. So with that, I guess, thank you.
Yes, thanks, Nikhar, for a great presentation. I think it's really great to see how far you've come with this whole ROSCO tool. Congratulations on that.
Thank you.
Yeah, questions. So we have 10 more minutes, I think, for questions. So if there are any questions, raise your hand, and then we'll give you the word. So Jan-Willem, you start.
Yeah, so thank you very much for your presentation. I really enjoyed it. Can you say something more about this stability margin that you put on one of your last slides?
Yeah, so this is, I guess, an idea somewhat rooted. It's been written about a bit. Frank Lemmer wrote a paper a couple of years ago talking about this idea that near rated operation, you could kind of tune your controller to satisfy some amount of stability in the kind of linear analysis sort of sense for a floating turbine. And then further above rated, you don't need to really be as concerned about the stability of the platform. And you can kind of target rotor speeds a little bit more and regulate your rotor speed without being as concerned about driving a platform unstable. And so I've done some work to kind of take this idea and automate the process of tuning that to say that we have a minimum rotor speed constraint and a maximum allowable bandwidth, and we'll fit basically a curve of natural frequencies to satisfy those constraints and subsequently get a gain schedule out of that.
So there is no link with Nyquist or whatsoever, the -1.
Yes, there is.
Okay, good.
Yes,
okay.
So that's basically the minimum stability constraint is how close to -1 you get in that Nyquist.
Perfect. Nice, thank you.
Yep.
Other questions? Please raise your hand. I see a question in the chat. Hi, Sebastian. On the what, maybe you can read on the horizon slide. What's the open loop feed? All right, then. Can you explain it a little bit more, Nikhar, what the open loop feed is for? What you mean with that?
So there's been some work to say if you have a turbine model and you know your future disturbances, so which in the simulation sense we always do, then you could choose an optimal controller using MPC is kind of like a version of that, I'd say. And if you have this optimal control trajectory and say that you want to specifically feed X set of blade pitch angles and Y set of torque controller inputs to just feed those through, you could use ROSCO basically as maybe a proxy to go from a table of these values to OpenFast or to Hawk2 or whatever simulation software you're using.
Cool, thanks. Another question from Adam Stock.
Hi, yeah, thank you for that. It was interesting. I did arrive a little bit late. Unfortunately, I was late out of another meeting, so apologies if anything I asked here was covered in the kind of 2 or 3 minutes at the start there. I was just wondering what the capabilities are regarding curtailment. So is there similar functionality to the Siemens Park Pilot style curtailment where you can just say, oh, I'm going to go to this level of power output and have that as your maximum?
So there's been some, I guess there's a branch floating around with some power reference tracking where you could kind of feed through what specific power you want. That is maybe I'd say in its preliminary forms, and that's the first steps towards a curtailment sort of scheme in ROSCO at this point.
Mm-hmm. Okay, and I just have one other thing as well, which, and you probably said this in the first few minutes. So, but does this use the kind of DISCON communication protocol that's common across fast?
Yes, it does.
Yeah. Okay, that's great to know, because yeah, I'm interested because as everyone here will probably know, we've got a bit of software we're developing, and we use that communication protocol for the controller we use. So that would allow us to work with you to put this controller into our software as well in the future. So that's good to know. So thank you very much.
Yeah, of course.
I myself have, there's one more question. Diana?
Yeah, thank you. Thank you for your presentation. It was very interesting. I have one question regarding the tuning process. I think you use a power coefficient mapping, which is run under the assumption of a rigid rotor. I think, does it make a difference when you are running elastic simulations and then you are not totally rigid? So is the path that you described with the rotor rigid rotor assumption good enough?
I guess in my experience, yes. I've tuned this controller for a number of fairly flexible turbines. I think one thing to keep in mind is that it's not so much that the reference comes from the CP surface, it's more just the gains themselves, but the references are still based off of the fully elastic model. So it's not that we're saying at above rated operation and at 15 meters per second, the blade needs to be at 4 degrees. We're just saying this is what the gains should be to achieve our reference rotor speed at above rated. That said, I think it would be very interesting to look at kind of a comparison of tuning this controller for using a kind of a rigid rotor to get the CP surface versus getting the CP surface with more fully elastic simulations.
Thank you.
Any final questions from someone? No, I don't think so. Then I think we can wrap up. Thanks, Nikhar, for your talk. And,
Yeah, thank you, everyone.
Hope to see
Appreciate it.